started here. So here's what I want to do today. So I want to go just a little bit more in depth to what we talked about last time. So last time we talked about free body diagrams. So that was the dot with the arrows to find the net force. So we're just going to go into a little bit more depth with that. At the end of today, we're going to do several practice problems together, and then there's going to be a couple that I ask you to do on your own, and then I will collect that at the end of the period. Pardon me. So just make sure that you're following along and are ready to turn that in later.
Wait, this is going on Schoology? Is this recording?
It is, yes.
I'm not gonna lie, Mr. R. I gotta use the bathroom, like, very badly.
Okay.
I'll be right back.
Make sure your microphone's turned off. All right. So if we let me go to my notes. So 2 days ago in class, or the last time we were in person, the day that the power went out, we talked about these 6 types of forces, right? And then what we did last time was we drew free body diagrams like this, the dots with the arrows, okay? What we're going to do to that is we're going to add some equations to that. So the notes for today, you can label them net force calculations. And there are 3 equations that you're going to need for doing net force calculations. 2 of them you've seen before. 1 of them you haven't. The first one is going to be the Newton's second law equation. Anybody remember what that is? By any chance? That's all right. It is F net equals ma is the equation. Does that sound familiar? The second equation is the weight equation. So weight is another word for force of gravity. And so the weight equation is that the force of gravity is equal to m times g, where g stands for the acceleration of gravity, which is 9.8. Now, when we use g, we're going to always treat it as positive. When we talked about acceleration last unit, we maybe talked about negative, it being a negative acceleration. But when we talk about g, we're going to keep it a positive number. And the third equation we're going to have is the net force equation. This equation looks a lot more complicated than it is. It's actually a very easy equation, but it's written like this. F net, give me 1 second. I'm going to let Gavin in here. F net equals minus V1, or sorry, plus minus F1, plus minus F2, plus minus dot, dot, dot. All right. Those are the 3 equations you need. We're going to do a couple practice problems together. So here's the first practice problem. You don't need to write down the problem itself, just show your work. So a horse named Epona pulls a 400 kilogram carriage with a force of 890 newtons. There is 115 newtons of friction. What is the acceleration? Ignore air resistance. Okay, so the way we do this, right, we always start our picture or our problems with a picture knowns and unknowns. But when we're doing forces, the picture means our free body diagram. Start with the arrows on it. So let's go ahead and start with trying to think about what forces would be acting on the chat. tell me what forces you think might be acting, either in the chat or turn on your microphone and tell me what forces you think are acting on this object. So, yes, Jacob, I agree. There's friction. Give me 1 second. Friction's here. All right, so we're going to have friction, which is going to go backwards. Gravity, yes. What else? Remember, for the normal force, so Mac is right, we're going to have a normal force, right? Anytime you're on a surface, there's also going to be a normal force that is going to balance out the gravity. And this horse is pulling it forward. What would we call that force that's pulling it forward?
Applied force.
The applied force, yes. So this is my free body diagram. The other thing we need to make the free body diagram complete is we're going to go ahead and draw the net force, and we're going to say the net force is going forward. So that's my picture for this case. Now we're going to do our knowns and unknowns. So I know my mass is 400 kilograms. This is probably my applied force, right? 890. Friction force is 115. And I'm looking for the acceleration. All right, so whenever we solve a problem, we're always going to use these two equations. We're going to use the top equation, and we're going to use this net force equation. These two equations we're always going to use. Sometimes we'll need the weight equation, but we're always going to use the first and the last equation. And the way that I recommend going about this is starting by writing them both out. So we know we got the equation F net equals MA. And we're also going to have the equation F net equals plus minus F1 plus minus 2 minus dot, dot, dot. Now, it looks like a complicated equation, but all it means, the dot, 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 either expands or contracts to include all the forces that are going in the same direction as the net force, right? So you can see here the net force is going in the x direction. So for this problem, the way we're going to write this equation is we're going to write it as plus or minus all the forces that are going horizontally. So plus or minus FA, plus or minus FF. Any forces that are going vertically, we're going to ignore those, because the net force is only going horizontally. Now, the reason why this says plus or minus is because we have to look back and we have to decide, is applied force going forward or backward? Is it going with the net force or against it? So anything that's going with the net force, we're going to make positive. So applied is going with it, but friction is going against it, so it's going to become negative. So this equation becomes F net equals FA minus FF. The next thing we can do is we can combine these two equations into one. And so we can say MA is equal to FA minus FF. And after this, it's just a matter of plugging numbers in. Mass is 400. I don't know A. FA is 890. FF is 115. So I think I get 400A equals, what is that, 775, is that right? Yeah, thank you. Thanks, Jacob. Right. Then I divide both sides by 400. That's how I get 1.9 second squared as the acceleration. Any questions there? This is really no different than anything we've talked about before. It's just putting things together, right? So it's just all we did was we took the forward force minus the backward force and we set it equal to mass times acceleration. All right. Shall we try another one? All right, stop me if you need this page still. I'm going to turn the page. Here's problem number 2. A bucket is being lifted out of a well. It has a mass of 4 kilograms. What force is needed to make the bucket accelerate at a rate of 7 meters per second squared? Sorry, number 2. So this is number 2. So just so that you can think about it, right? We're imagining a bucket, and let's just imagine that it's being lifted by a rope. So there are 2 forces acting on this. What do you think they are? Tension, yep.
Applied force?
Well, so we could either call the upward tension or applied. If we're thinking about it as coming from a rope, it'll be tension. I'm going to call it tension, or you could call it applied. And yes, Dayton's got the other one. The other one's going to be gravity. But the key is if I'm lifting it, up has to be winning. So same thing we did last time. We're going to set up both whoops. Let's do knowns and unknowns first. Mass is 4. We're trying to find the tension force that I need to accelerate at 7. We got our 2 equations. We got F net equals MA, and we have F net. This time, F net's going to be equal to what minus what, do you think? Remember, you go, anything that's going with the net force is positive. Anything that's going against the net force is negative. Everyone got an idea about what this one's going to be? And we know our 2 forces are FT and FG. Is tension going to be positive or negative? You know, it's going with the net force, so tension is going to be positive. Gravity is going against it, so it's going to be negative. So this equation becomes F net equals FT minus FG, and then I combine them. There's one other thing we can do, right? Do we know what force of gravity is equal to? Yeah, we don't know a number, but we do know this, right? We know that force of gravity is equal to mg. So what I can do then, oops, that there. So what we can do then is we can say this is equal to ft. I'm just going to plug in mg for fg. And then it's just plugging numbers in. So 4 times 9.8 is, I think, 39.2. So I add 39.2 to the other side. I think we get that. Any questions?
I have two questions. First off, where the heck did you get the N on the end of 67.2?
Good question. It's a force. Forces are measured in newtons.
All right.
Yeah.
And second one,
Yeah, real quick before you go on to that, let me say something about that real quick. Yes, forces are always going to be measured in newtons. Accelerations will always be meters per second squared. Masses will always be kilograms. All right, second
okay.
question, Tristan, go for it.
This one's probably a dumb question, but F net, does that always just go with the biggest force on like the chart?
Yes, because the net force points in the direction that's winning. So yes.
All right, thank you.
I ain't gonna lie. I missed the first one because I was in the bathroom. Can we go back to that one?
I'll post the video when we're done, and you can look at it on the video later. All right. Any other questions about 2? All right. I'm going to have you try one. So I want you to try to start number 3 by yourself. Number 3 says, you and your friend are able to use a rope to pull a giant cement statue across the ground at an acceleration of 0.7 meters per second squared. Sorry, 0.07 meters per second squared. If you could apply a combined force of 980 and the force of friction is 300, what's the mass of the statue? So let's go ahead and I'm going to have you try on your own on your paper to do a free body diagram, so the dot with the arrows. When you think you're ready, put one force you think I should draw in the chat.
Tension.
Yeah. Going forward, right, Tristan?
Yeah.
And so we're pulling for gravity, yes. So Mac, I could call it the applied force if I wanted to. Since it's a rope, I'm going to call it tension. But the other thing could be, if you wanted to think of it about actually being pushing, that would be the applied. But yes, we're going to have gravity. So Jacob has gravity, and Jacob also has friction. I agree with that. One more. Yep, that's right, Mac. So I want to surface it's normal. Again, I'll go ahead and say my net force goes forward. So in this case, as far as what I know, right, I think I know acceleration. Let's see, we got tension, friction. I want to find mass. All right, see what you can do with this. keep working through it, and then we'll talk about it in a second. So the first equation is always F net equals MA. Anyone want to take a stab at what the second equation is going to be this time? It's always going to be what's ever going with the net force minus whatever's going against it. So what's going with it is tension, right? Minus whatever's going against it is friction. Again, we ignore normal and gravity. Yeah, Taylor, that works. Yep, good, good, good. All right, we got it. So yeah, so we ignore the upward ones because the net force is going horizontally, right? And then we can just combine these two. Sorry. Yep, that's what I got. And yes, it's kilograms because it's a mass. So Tristan, I'm glad you brought that up earlier. It probably is helpful to have this in your notes, right? Force is always in newtons, accelerations meters per second squared, mass is in kilograms. All right. We have about 13 minutes of class left. Let me explain what I want to do. So if you look here, right, in today's folder, there's a day 37 assignment. Sorry, Grady. Sorry. So there's a day 37 assignment. So there's 2 more problems I'm going to ask you to do. So if you actually click on this, we just did 1, 2, and 3. I'm going to ask you to do 4 and 5. Grady. So I'm going to ask you to do 4 and 5 in your notebook, and I'll also put it on the screen here for a second if you'd rather look at the screen. But this 4 and 5, I'd like you to do and then turn in when you're finished. But we're going to stay here on Zoom so that you can ask questions as they come up. And the deal is going to be you need to finish these 2. When you're finished with them, and they're right here too as well. When you're finished with these 2 problems, you get to upload them to Schoology, and then you are free after that. So you can log out after you've uploaded these to Schoology. But I want you to do these on your own, and as questions come up, you can ask them. So we'll stay on Zoom here until you get this turned in. Deal?
Sam said nah.
Do people find Grady more annoying in person or electronically? Both? Okay.
Okay, guys. Okay. Okay, I see how it is. Okay. Okay. Okay.